So we turn from the subject of just maximizing and minimizing things to this idea in calculus that we often want to do, which is to optimize a function subject to some constraints. You might remember the old problem of the farmer, right, who's got a certain amount of fencing, like 100 feet of fencing, and wants to make the biggest pen that he can, the largest area that he can, a biggest sheep pen. So in multivariable, we do something a little different because we're working with larger functions. And so we're going to introduce this new method of Lagrange multipliers. So let's just define our problem. What are we doing in multivariable? Well, we're going to say that we're going to try to optimize, that is maximize or minimize some function, f of x, y, z, subject to some constraint, which is a different function pegged to some value. So again, we've got our two functions here. We've got the one that we want to optimize, and we've got our constraint, which is also sometimes called a side condition, our constraint g. So as an example, and this is the example we're going to be following today, let's say I want, instead of a sheep pen, let's say I want to have a box, and this is going to be a box like this. It's going to have sides x, y, and z, and the idea is the top of the box is open. And what we want to do is we want to maximize the volume of the box, which is x times y times z, subject to this constraint that the surface area of the box is equal to exactly 12. So in this case, what would our surface area function be? Well, we've got 2xz, because we've got two of these sides, plus 2yz, we got two of these sides. And like I said, the top is open, so we just have a single xy here. And that function is going to be equal to 12. In this case, then this is our f, and this is our g, our constraint. So how do we do this? Well, take a look at this little diagram that I've got over here. So on this diagram, I have labeled in orange over here a bunch of different level curves of our function, 7, 8, 9, 10, right, whatever. They could be any values, but let's just say we're doing this from some arbitrary function. And on the left side here in pink, I've got the level curve corresponding to my function g, right? I've got my constraint curve. Well, if you looked at this and asked, what's the biggest value of f subject to the constraint, you would probably come up here and conclude that at this point, f equals 9 is the highest value of our function subject to the constraint g. And I want to point out something that's really, really, really convenient, but also really, really clear here, well, hopefully clear, is that at that point, whatever that point is, here it would be like x0, y0. At that point, whatever it is, the level curves g equals k, and the level curve of f are parallel. Or I guess more accurately, they share a tangent line. They share a common tangent line. That the tangent line to the curves, to both curves at that point, is the same. Now, this has a certain sensibility to it. And one way to think about that is if we're, imagine, moving along our constraint curve and moving along g, at this maximum point, if we're moving along g, you could imagine that the directional derivative of f along curve g should be equal to 0. And this is kind of another way in calculus we say over and over and over again in different ways, from AB to BC to other things, that you have a maximum or a minimum where your derivative is equal to 0. In this case, it's the derivative along our constraint curve. if they share a tangent line, though, that also means that their normal vectors, the normal vectors to the curve, are parallel to each other. So the normal vector to the curve G and the normal vector to whatever level curve of F are parallel. And we just learned in our last section about normal vectors to level curves. So it might not come as much of a surprise to you that I'm going to write like this, that in order for us to have a maximum or a minimum subject to a constraint, what has to be true is this, that the gradient of F, I could write, the gradient of our function F is equal to some scalar, which we'll call lambda here, times the gradient of G. For some scalar lambda. And this, it turns out, actually is the core of what we're doing. And this is called the method of Lagrange multipliers. And in fact, this number, this scalar number lambda, is in fact called the Lagrange multiplier itself. Why does it have to be like this? Well, what we're really saying is that they're parallel, right? And two vectors are parallel if they're equal to a scalar multiple of each other. So the gradient of F is some scalar multiple of the gradient of G. So we're going to set up this following method, and we're going to do a little example here with this box. The first part of this method is to find our gradients. Find the gradient of F and the gradient of G. The second is to set up a system of equations. And it turns out that the equations we need are the equation, the gradient of F is equal to lambda times the gradient of G. But we also are going to use our constraint, G equals K. And we'll show how to do that. And then the third step, which is both the most straightforward and the hardest of them all, is to solve somehow. And this is where I'm here to tell you that there is no single method for solving these systems of equations. We're going to see a bunch of different examples where we do a bunch of different things. Sometimes we're going to solve for x, y, and z. Sometimes we're going to solve for lambda. You're just going to have to go along for the ride and see how it works. So here we've got our example, right? We've got our box. The volume is given to us by x, y, z. And we're trying to find the maximum volume subject to this constraint that the total amount of cardboard or whatever we have to work with, total amount of stuff we have to work with is like 12 square meters or whatever. Let's just stick a unit on this, 12 square meters. That 2xz plus 2yz plus xy equals 12. So let's go ahead and find our gradients. We're going to start with the gradient of v. Okay, if I take my derivative with respect to x, I get yz. With respect to y, I get xz. With respect to z, I get xy. And the gradient of my surface area is going to be, let's see, with respect to x is 2z plus y. With respect to y, gets me 2z plus x. And with respect to z, gets me 2x plus 2y. So here are my equations. I've got the following equations, right? And again, if these vectors are going to be parallel, that means I can look at each of the components. So if I look at my first component, I'm going to get yz equals lambda times 2z plus y. If I look at my second component, I'm going to get xz equals lambda 2z plus x. I'm going to get xy equals lambda 2x plus 2y. And my fourth equation is my constraint equation. So I guess I can actually just write 4 up there. My fourth equation is my constraint equation. So we will just sit by with that. Okay. So again, there's no clean way to necessarily solve this every single time. I could solve for lambda and set my lambdas equal to each other. In this case, I'm going to exploit a little trick which comes up from time to time. You'll notice that each equation is missing something. This first equation is missing x, y, and z. So what I'm going to do is I'm going to multiply both sides by the missing variable. And the reason to do this is that now if you look at the left sides, they're all the same. They're all equal to x times y times z. So I'm going to take equations 1 and equation 2 and set them equal to each other. So I'm going to ignore the left side and just take the right side. So I'm going to get lambda times 2xz plus xy equals lambda 2yz plus xy. All right. And now I'm going to divide both sides by lambda. I'm going to divide lambda away. And it's worth stopping here for a moment and putting on our thinking caps and saying, is it okay to divide both sides by lambda? If we want to divide both sides by lambda, we got to stop and ask ourselves first, what happens if lambda is equal to 0? Well, let's take a look. If lambda is equal to 0, then any one of these equations is just going to turn into x times y times z equals 0, which is the same as saying volume equals 0. This is the case that you're going to get if you decide that, you know, x is equal to 0 or y is equal to, like, one of the dimensions is equal to 0. And if you choose one of the dimensions equal to 0, you can certainly find a surface area, but at that point you don't have a box anymore, you just have a sheet of flat cardboard. So it's okay. We don't need to consider, in this case, lambda being equal to 0. So in this case we get 2xz plus xy equals 2yz plus xy. Hey, look, my xy's cancel, my 2's cancel, and my z cancels, and I get x equals y. Awesome. I figured out that x is equal to y, that these two dimensions on my box need to be the same. If I repeat this and I look at, say, I don't know, equation 2 and equation 3, I'm just gonna get rid of my lambda right away to save space. I'm gonna get 2yz plus xy equals 2xz plus 2yz. My 2yz's cancel out, my x cancels out, and I end up with y equals 2z. And now I'm a little stuck. I've got x equals y and y equals 2z. And I might not know what to do from here. And the answer is, I've got all the relationships between my variables. And at the very end, once I've done that, now I'm going to come back to my constraint. And I'm going to say that I know that 2xz plus 2yz plus xy equals 12. So in this case, I'm going to put everything, I don't know, in terms of y. Z equals y over 2 is the same here. So I'm going to put everything in terms of y. So I get x equals y, z equals y over 2, y over 2. X and y are the same, so this is y squared equals 12. So let's see, what do I get? I get y squared plus y squared plus y squared. I get 3y squared equals 12, which is the same as saying y is equal to 2. If y is equal to 2, so is x. And y equals 2z, so z is equal to 1. So it turns out that if I have 12 square meters of cardboard to work with, the correct dimensions for my box are 2 by 2 by 1. It is wide and a little squat. And I just want to note a convenient thing, and we're going to do lots more examples of this in class. And this is, in fact, the same example from your book if you want to follow along. One of the things that I think is really neat about the method of Lagrange multipliers is the equations we did, the methods we did, don't know that this is a box, right? They don't know what the physical application we're doing here. But one thing that's kind of neat is that I just want to note that x and y are on equal footing. And when I say that, that's maybe a strange thing to say. If I look at my volume equation, the function that I'm doing, it's just x times y. If I swapped x and y, it would be the same. It would just be x times y times z. And similarly for surface area, if I swapped x and y, it wouldn't matter. It's still multiplied by 2 here, and it's just x times y. That my equations treat x and y as being the same, as being interchangeable. And it turns out that when you do that, the optimum solution is just to have them be the same. And you'll find this over and over and over again, that if two variables are treated equally in the equations, the Lagrange multipliers are going to spit out, well, okay, well, those two things are just going to be the same. So we're going to, again, see lots more examples of this in class. We're going to be optimizing lots of different functions subject to different constraints. This method of like making all the left sides look the same and then setting the right sides equal, we're going to see that approach again. We're also going to see some other approaches that are going to be a little bit different. We're going to see times when lambda is equal to 0 or not, or there's multiple possible values of lambda. Sometimes we don't even care what the value of lambda is. We actually didn't look for it here at all, and it didn't matter. And so I really just can't drive home enough that there is no one way to solve problems of Lagrange multipliers, but you should trust you've got 4 equations, 1, 2, 3, 4, and you've got 4 unknowns, x, y, z, and lambda. You've got enough equations to solve it exactly. You just have to trust that there is a method. So we will look at lots more examples of that, like I said, in class.